In the first lab, we were told to experiment with a real-life object moving with constant velocity. The goal was to observe this object, obtain a plot of the data of the motion we analyzed from a program called Tracker, and compare it to a predicted computational model on a program called VIDLE. In order to do so, I decided to move a 0.227 kilogram cylindrical popcorn can across a table in the negative x direction. After comparing my model versus the computational model, I was able to determine that the velocity of the moving object was constant because there was no net force acting on the ball. Newton's second law states that the acceleration of an object is dependent upon two variables, the net force acting upon the object and the mass of the object. Acceleration can be defined as the change in velocity over the change in time, and that brings us to the equation final velocity is equal to initial velocity plus the net force divided by mass times the change in time. Therefore, in order to have constant velocity, the acceleration must be equal to zero, meaning that there will be no net force acting upon the system. From Tracker, I was able to take data of the motion of the object along its center of mass. I observed that the position versus time graph was linear, showing that the velocity of the object stayed constant and did not change over the duration of the object's movement across the table. The slope of the graph is negative because I chose the positive x direction to be the right and the negative x direction to be the left, and I moved the object from the right to the left. The data from Tracker was also able to show me the initial position in time data and the final position in time data. The movement of my object started at an initial position of 0.0178 in the positive x direction at a time of 0 seconds. In order to calculate initial velocity, I took another point and found the change in position over the change in time. From this, I was able to calculate the initial velocity to be negative 4.56 meters per second in the negative x direction. Using Newton's second law and plugging in 0 for the net force, I was able to calculate that final velocity was equal to the initial velocity. From the data I obtained on Tracker, I changed some parts of the standard code given to us to create a computational model. I set my initial position of the ball to 0.0178 in the positive x direction, the velocity at negative 4.56 in the x direction, and input a new mass. The time was set to start collecting data at 0 seconds and iterate within a while loop on intervals of delta t of 0.01 seconds until it reached a final time of 0.916 seconds. I set the net force equal to a vector quantity of 0, 0, 0, and coded Newton's second law stating that final velocity of the ball is equal to initial velocity of the ball plus net force divided by mass times delta t. In order to find the new position at different time intervals, I also coded that the new position of the ball is equal to the initial position of the ball plus the velocity of the ball times delta t. From this code, I was able to produce a computational model. The picture on the left shows the can traveling in the negative x direction, and the picture on the right shows the position versus time graph of the can's motion. As you can see, the slope is linear, showing constant velocity. Afterwards, I plotted both the data from the computational model along with the data from Tracker to create a graph and compare both the predicted and experimental model. From comparing both graphs, we can prove constant velocity because both of the slopes are negative and linear, and there is a net force of 0 acting upon the object. Any error in the model from Tracker could have been due to a small force of friction acting on the object as it moved across the table. If by chance the axes were flipped, the object would have traveled in the positive x direction and the sign of velocity would have been positive. Overall, from this experiment, we cannot tell how many other forces were acting on the can, but as long as they cancel each other out to give a net force of 0, the velocity will always remain constant.